Good morning, folks. We're back to POV-Ray, Persistence of Vision Ray Tracing Program. If you know scene description language, I'm scrolling through it on the left. There's all these spheres and cylinders at the bottom, and at the top we have to set up lighting where the camera is. Now I can check off some already generated scene description language files, which are called POV, extension POV, and just say run them all. And you see randomly generated tetrahedra. I'll show you in a second how I got these. And that's kind of an XYZ coordinates apparatus at the center in gray. The tetrahedrons are orange. And I'm rendering them, batch rendering them from the unofficial GUI for the Mac for POV-Ray. It has an official Windows GUI, but this is a Mac right now. So now we're switching to Python for High School, where I'm doing this as part of a presentation on Bucky's concentric hierarchy of volumes, which has some more whole numbers in it than we might be used to. But how do we get there? We learn what a generator is in Python. We apply it to simple things like the Fibonacci sequence. We make sure to pair up with the online encyclopedia of integer sequences. That's a resource we keep jumping to as we develop various historic and important sequences. Of course, you can always experiment, maybe come up with your own sequences. And from Fibonacci, we move to this famous sphere packing formula, which Fuller gets credit for usually. Maybe other people thought of it too, of course. Pretty much true with any great thoughts. And by this time in our high school, we've already come through some of these exercises. We understand already at this point about the 1, 12, 42, 92 sequence. We've checked it out in the online encyclopedia and so on. So then we build in Martian math. We build a turtle class. It's like a turtle in Logo. It's going to swim in, you could say, the IVM ocean. It's going to have dunder next and dunder iter methods. By the way, this food cart, where you see a cow being abducted, it's actually a food cart, and I'm showing where in my neighborhood on Hawthorne Boulevard this food cart exists, right across from the Linus Pauling House. Okay, place-based education. So I'm going to embed this video in this very Jupyter notebook as explanation. I've been telling my students and teachers, other teachers, that there's great pedagogical value in having a Jupyter notebook with an embedded YouTube about that very Jupyter notebook. Right? So that's a caltrop. I'm scrolling past the caltrop and seeing if I can get the right size. This is a stand-in for our quadray coordinate system, where we just have 4 arrows pointing away from an origin, and there are 4 tuples. In other words, we don't use XYZ 3 tuples, we use 4 tuples. And in our turtle experiment, we're going to create 4 iterator turtles that every time you say next, every time you nudge them, they're going to pick one of 12 directions to jump in, i.e., in other words, to a neighboring ball in IVM or CCP. So every ball is surrounded by 12 other balls. And I've got these color coordinated things in Wikipedia and stuff to help. So we're going to start with 4 turtles at the center, and we're going to let them iterate. We're going to let them jump randomly in 12 directions each time for, say, 30, 40 jumps or less, possibly, and then we'll get the volume of the tetrahedron at the end of all those jumps. In other words, each turtle gets to wander around randomly going in one of 12 directions. So in other words, jumping from ball to ball within the CCP, giving us a random tet. There we're experimenting 400 jumps. And so random tet there is 500. Now you'll see there's some rounding issues, and I can round it up. I need to come through here again with a different number type other than floating type to show that these results are exact and they are integers, they are whole numbers. And that's a somewhat surprising thing, that these turtles swimming around in the CCP give us whole number volume tetrahedrons. And if you check it, you'll find it seems I'm wrong, because you won't get that. And the reason is I'm using tetravolumes. 4 balls packed together and 4 CCP balls, same diameter as the so-called ocean or IVM matrix. Same diameter, and so that calibrates my unit volume, 4 of those. So 5 unit volume means a tetrahedron of 5 tetravolumes. So here's where I'm actually generating the POV files in a Python program called POV.py. I start with the 4 quadrays and the 3 XYZ vectors, positive vectors, and I use the incoming coordinates to convert, because I don't really do any quadrays here. In theory, I only have XYZ, but they're preset to the 4 quadray positions. So I compute on the fly what the scene description language would be, multiple frames with multiple volumes, computing at random. I mean, the turtles move at random, and then I get the volume at the end of the day. So you see my output here, all whole number volumes, and this relates to, well, that's pretty much a summary of the code there. This relates to my slideshow. This is one of the slides. If you go back a couple videos, there's another version of me narrating the entire slideshow. This is just one of the slides, upper right there. It was same idea. See, the tetrahedrons can assume random positions. The corners can be randomly in the CCP. I'm jumping around here a lot, I realize that. And you'll always get the same whole number volume. Here's from Wikipedia quadrays. So the yellow is the cuboctahedron. And in this slideshow, I elucidate in more detail where this math is coming from and how it sort of jigsaw puzzle fits into 1900s and now 21st century culture. Buckminster Fuller et al. So I invite you to check out the notebook where this is at home. And Python for High School is the course here. It's a great little course, recommended for anybody, even if you're beyond the high school age.